All right. Hello, everyone from the future, maybe. So this is the Thursday, July 16th class. You've got your previous due dates as well as 4.5. We do on the 23rd. You might have noticed that date was the 21st in my math lab. I changed it to the 23rd. I also put 4.6s up there as the 28th. I'll put a question mark there for now. You already know today's class is pre-recorded. So again, hopefully nothing's going to be too different. This will be slightly shorter in length. I want to hit a certain point in the material and then I need to call it a day. I want to point out that after I take care of the family thing I've got going on Thursday, I will be going out of town. And I will be in a place without internet access for the weekend, for Saturday and Sunday. So if you email me, I probably won't get back to you over the weekend. I won't get back to you until Monday morning or maybe late Sunday night. But still, please email me if you have any questions. We are getting close to the end of the class. Probably next week, we'll start talking about the final exam. I also need to talk about test 3. They're going to be pretty close to each other. The final exam will only be a one-day window. Please note that. So test 3, you'll still get a couple days, but the final, you're only going to get one day. And I'm likely to not hold an official class on the day of the final exam since, well, we wouldn't have a regular class on the day of a final and under normal circumstances. All right, but I don't want to waste too much time. Like I said, we'll start talking about those details next class for both of those. Let's pick up where we left off, which was 4.5, the substitution technique. So we said we need the substitution technique at times because there's no product rule, there's no quotient rule, there's no chain rule for integration, whereas we have these things for derivation. In fact, not all functions are integratable or anti-differentiable under normal rules. Sometimes you have to just go to complete numerical analysis, or sometimes you have to use these weird fancy techniques that they teach you in grad schools. And after that, integration is a much more complicated idea than derivations, than derivatives. And we did some examples. We talked about how you have to make a let use statement, kind of like you did back in pre-calc to change variables over. But then there's a couple extra steps. You had to take its derivative. You had to use the differential form, the du over dx. The du and dx are differentials independently. Then you multiplied both sides by dx. We start trying to treat this like a fraction, and then divide by whatever's next to the dx. Those two last steps are just basic linear algebra that everyone should know how to do. It just looks a little ugly. So the two things you need to have are a u equals and a dx equals. You plug those two into your original integrand, your original integration. And if everything works appropriately, if you did the right substitution and substitution was the appropriate technique, you will notice that all the x's go away. You may be stuck with an extra ugly constant, but these things boil down to something much simpler, like this ugly integral turned into the integral of u to the 4th. And this ugly integral with an appropriate substitution turned into the integral of u to the 8th over 4. Oh no, over 4. That's terrible. Sarcasm. And then we just have to remember that after we integrate, we go back to our original variable. Go back to the original variable. And then I also pointed out that what's interesting is you might say, okay, well, if we can integrate this x squared plus 3 all raised to the 4 times 2x, you could probably do it if the 2x wasn't there. And in fact, we don't know how to handle that yet. Well, I did say that you could expand this thing to the 4th power, but that's kind of a pain. Nobody wants to have to do that. And then the same thing goes for this one. Without that x cubed, this would be a massive pain in the butt to have to do. And that's the one I think I said would take you probably a half an hour plus. And you got to have really good bookkeeping skills to even still get it right. So what's interesting is you might have the parentheses part, but you're missing this part, and then you can't actually integrate it. Now, I'm not going to give you those problems, but they do exist. So the last thing we did was I said, well, think about this one versus that one. The left one's uglier than the right one, but in fact, because this x is down here, it makes it a prime candidate for substitution because the variable that you'd be doing your substitution on, this x squared, the inside part generally speaking, you can also say that with polynomials it's generally the higher power part. Because this is 1 degree lower, that means when you solve for the dx and plug it in, it'll cancel this x out. Whereas in this format, that doesn't happen. And this is one of the classic first examples of an integrand you can't do, well, classically. What's the term? Sorry, I blanked for a second. I was thinking about something else. Transcendental functions. So when we talk about transcendental functions, they're the things that we're used to dealing with basically. And then we can integrate this type, but not this type, even though it looks simpler. Just kind of interesting. So that was the spoilers. You can do the left, but not the right. And the next example we're going to do is the one on the left. So for C, and under orange, I want to stick with red. Also, I'm using only one hand today, and that's probably going to be true for the rest of the semester. I've been dealing with a pretty bad injury, and it's just getting worse, and my right arm is not really very good right now. So it's fun using a mouse with your left hand. Good thing is, I am actually left-handed, so it doesn't affect my writing ability. You might say, well, you probably should have been right-handed with that terrible handwriting. And I'd say that's a great joke. I've made it myself. But I don't really have much experience using a mouse with my left hand. But anyways, we're not going to let that get us down. We're going to keep going on. So the integral of x e to the x squared dx. And I pointed out last time, the x could be behind it. This would be the same thing as if the x, instead of being in the front, was behind it. So you've got what feels like a product rule, so we probably need to say let u equals, and I was supposed to do that in black. The problems are supposed to be in black. Red is for the writing. Third tie is the charm. Integral x e to the x squared dx. There we go. So we say let u equal, and I said it's generally the inside, or if you're dealing with a bunch of different polynomials that are all over the place, you usually want it to be the higher order polynomial part. So it's definitely the x squared. If you say let u equals x, you're going to very quickly find out that nothing works. Then you take its derivative, but you have to do it in the form du dx. If you don't like the letter u for substitution, the second letter of sub, you could use y or z or whatever you like. The derivative of x squared is 2x. We multiply both sides by the dx, so we get multiply both sides by dx to cancel the one in the bottom. So that'll give us du equals 2x dx. And then we're going to divide both sides by the 2x because we're supposed to be solving the 2x, writing and talking. Divide by 2x because we're supposed to be solving for dx. And what that gives us, finally, is that du over 2x is equal to dx. And it is this that we have to plug in along with this. Instead of the instead of the x squared, we'll write u. Instead of the dx, we'll write du over 2x. So this integration is going to become the integral. Now I'm not changing the x stays for now. The e to the x squared part is what I'm going to change to u. And then the dx is changing to the du over 2x. And I'll do blue what I changed. So the x squared turned into a u, and the dx turns into du over 2x. Now the 2 doesn't cancel, but the x's do. This x cancels with this x, which is exactly what you need to see. So this is the integral of e to the u over 2 du. Or you can pull that 2 out of the integration. 1/2 integral of e to the u du. This is a super simple formula. The integral of e to the u is e to the u. So this is equal to 1/2 e to the u, but don't forget your plus c because there were no upper and lower limits. But then we have to go back. So instead of writing u, we write x squared. So this is equal to 1/2 e to the x squared. plus c. That's our answer. All right. Now, like I said, I'm going to go a little quicker here. I might talk a little quicker. I've got a lot going on, and I'm barely able to even cram this into my schedule, but got to do what we got to do. The cool thing is, if I go too fast at any point, when you're watching this on YouTube, in the bottom right of the actual video, there's a little wheel, that's the settings. You can go under that, and you can change the playback speed. You can slow it down to 0.75 or 0.5. So if I'm talking too fast and I just blah, 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 you can slow it down and get me at a better pace. You also have the rewind ability. Use it wisely. All right, D, the integral of. Now this is where we're going to get a little weirder, and this is why I said typically, not every time. This is going to be the natural log of x in parentheses squared, then over x dx. Now, I'm writing the dx in the top of the fraction. It could be to the side as a multiplier. It works either way, but I will write it this way. The integral of the natural log of x all squared. So that 2 is not part of the x, and it cannot be made as a coefficient. You cannot bring the 2 out as a coefficient. This is not that classic problem because it's outside. If the 2 is here, then you could bring it out as a coefficient. That's the major difference there. So let's scroll back up, and we said, where did I write it? Here it is, hint. The substitution is usually the inside or the bottom, and if there's a lot of stuff in the bottom, it's the inside of the bottom. Usually does not mean every time. All right, so here, I mean, you've got a top and a bottom, so what should the u be? Should the u, I'm going to erase this in a second, be the x, or should the u be the ln of the x, or should it be the ln of x all squared? Well, the last case is the least likely because that's the inside and the outside. Typically, that's not how we do a substitution. So that's definitely not it. So is the u the x or the natural log of x? Well, let's do this wrong. And again, I'm going to erase this in a minute. This is going to be wrong. If you let u be x, then du over dx, the derivative is 1. Multiply both sides by dx, and you get du equals dx. So this right here will turn into a u. This right here will turn into a du. But this right here is going to be stuck, and it won't go away. So that's clearly a bad substitution. So we did that wrong. So we say it's probably the u equals the natural log of x. It's probably the other one out of that. We gave a reason why the last one was garbage. We just showed why the first one is garbage. So let's let u be the natural log of x. And let's see what happens. So we're going to let u equal the natural log of x. So what that says is the derivative is 1 over x. You've got to remember your 4 or 5 basic differential rules. You never get to forget them. The derivative of a natural log is 1 over x. In this chapter, we've been saying that the integral of 1 over x is the natural log of the absolute value. We didn't need the absolute value for the derivative. So that's pivotal. Multiply both sides by dx. Now, some people might say, well, just flip this. And yeah, that technically works here, but it's too generalized. So let's multiply by dx to get rid of them on the left, which will give us just du is on the left equals, and now this is dx over x on the right. Now, I've been saying so far divide both sides by what's paired with dx, but this is actually a division. So think about your basic algebra. Don't divide this time. Multiply both sides by the x. That way, that x will cancel with that one. And what we end up with is x times du is equal to dx. This is what we need to see. It's solve for dx. So what we do now is we plug the let statement in. Instead of writing any natural logs of x's, we write u. And instead of writing dx, we're going to write x du. Those are the two things we're plugging in. So our integral becomes Here's the integral symbol. Instead of writing natural log, we write u. So this is u, and I said I'd do the substitutions in blue. So u, the square is still there. I don't really need the parentheses anymore though. Then over, the x is still there for now. The dx gets replaced. What is dx? It's x times du. So this is times x du. And look at that. Holy cow, the x's cancel. Gone. Gone. They're different colors though, so I don't want to show the slashing. So this is now just the integral of u squared du. Perfect. I don't know why I care that they're different colors. That's silly. I did it before. That's a terrible crossout. The integral of u squared, just add 1 and divide by the same power, so that's u cubed over 3. Don't forget your plus a c. But then we go back to x's. So instead of writing u, we write the natural log of x. So this is parentheses, and you need this parentheses. Natural log of x all cubed, because without the parentheses, it's implying something very different. All over 3, and then a plus c. And boom, there is our integration. Pause if you still need to think about this. E, the integral. All right, big fraction, x cubed plus x squared, all over, parentheses, 3x to the 4th plus 4x to the 3rd squared. And then I'll put my dx to the side. Or I could wrap the top in parentheses and put it in the top. That would be fine as well. So this looks like an integration of a quotient. Probably need a let u equals. What do we let u be? There's a top and a bottom now, so is it the top or is it the bottom? Well, more often than not, and notice I'm not saying every time, more often than not, when you got a top and a bottom, u is typically going to go with the bottom. But we showed you why it failed last time, and it's okay to fail. You get back up, and then you try something different. You don't just stare and let an hour or two go by. So let me spoil this. Write this down, even though I'm not writing it down. Whenever there's a natural log involved with integration, that is usually the substitution. I'm lying. I'm going to write it. Usually, more usuallys, if there's an ln of x in your integral, let u equal the natural log of the x, or whatever it is. The reason being, excuse me, is you're going to, when you do it that way, the derivative is going to be 1 over x, which means the dx will be x du, and then it can cancel with an x that's in the bottom. Now, the natural log could have been in the bottom as well, but you still needed that x in the bottom to cancel in the dx factor. All right, so if you let u be the x cubed plus x squared, that says the derivative would be 3x squared plus 2x, and I don't see anything remotely like that anywhere, so that's probably not going to help. And I also said that with polynomials, you usually need to let it be the higher part as well, the higher polynomials. So let's go with the 3, oops, wrong color, 3x to the 4th plus 4x to the 3rd. Not just the first term, you need it to be the entire inside. So that will say that du over dx is equal to, drop the 4 out in front, multiplied by the 3, 4 times 3 is 12. And then decrease the exponent by 1. Again, that was 4 times 3 times x cubed, the 4 times 3 is 12. Then plus, drop this 3 out front, so it's 3 times 4 times x squared, but the 3 times 4 is also 12. So 12x squared. That's kind of nice, believe it or not. Now what we got to do is multiply both sides by dx. So du over dx equals the 12x cubed plus 12x squared. We're going to multiply both sides by dx. Because of the multiple terms, you got to wrap it in parentheses. Your dx's cancel. So what we get is du is equal to, per the parentheses, 12x cubed plus 12x squared dx. Then we divide both sides by the parentheses to solve it for dx. I'm going to have to squish this in here, so I think you get the idea. I'm dividing by the parentheses so that the parentheses will cancel, giving us that du over parentheses 12x cubed plus 12x squared. That doesn't look like a 3 now, but it is. 12x cubed plus 12x squared equals dx. Honestly, the parentheses is unnecessary here because there's nothing else going on in the bottom, so I can't erase it, but you could leave it if you like. Pardon me. All right. So our original integral, what are we replacing? This inside of the parentheses becomes a u. This dx becomes this du over 12x cubed, blah, blah, blah. Those are the replacements we're going to see. So what we get is the integral. I'm leaving the x cubed plus the x squared in the top alone for now. Over. Then the parentheses, the inside of that is now just u. So because it's just a single term, I don't need the parentheses anymore. So that's u squared, and I said I would change colors to show the substitutions. So that's what changed. And now the dx is now this thing, this du over blah, blah, blah. So this is times du over the 12x cubed plus 12x squared. Okay, so x cubed plus x squared in the top, 12x cubed plus 12x squared in the bottom, they don't cancel each other out. The x's don't cancel, do they? Not yet. But what you can note is, in this bottom here, there's a GCF of 12. Pop that out and see what happens. So we get the integral of x cubed plus x squared over u squared times du over 12 times x cubed plus x squared. Now they cancel. That matches exactly that parentheses. So all your x's are, what's going on? All your x's cancel. So you have the integral of 1 over u squared times du over 12, which is just the integral of du over 12u squared. Or you can rewrite that as the integral, of 1/12 times the integral of du over u squared. Some people don't mind having the 12 in the bottom in the integrand. Some people like to pull it out. It's up to you. It's one and the same. I don't care. Well, that u is in the bottom, so we need to bring it to the top. So this is 1 over 12 times the integral of u to the -2 du. And then we add 1 and divide by the same power to actually integrate. So this is 1/12 times u to the -1 divided by -1 plus our c. Let's just make that a -12 in the bottom. In fact, let's just pull a negative in front of the whole thing. So negative u to the -1 over 12 plus c. Let's bring the u to the -1 to the bottom. So this is -1 over 12 times u to the first. I will write the 1 here for clarity, plus the c. But we got to go back to x's. So final answer, negative fraction 1 over 12 parentheses. We said that the u was 3x to the 4th plus 4x cubed. So 3x to the 4th plus 4x to the 3rd. Now I don't really need to write that 1, but I do need the parentheses because of the 12 in front of it, and then we have our plus c, and that's our answer. Yes, the negative could just be in front of the 12. Yes, the negative could be in front of the 1. Yes, the negative can be in front of the whole fraction. There's 3 good answers for how this can be written. This is my favorite version of it. So this one was a little more involved. There was a little more going on, mainly because of the GCF and having to pull it out, as well as we hadn't seen one of these in class in a couple of days where the u was in the bottom. You had to bring it to the top. Negative exponents, bring it back to the bottom after the fact. You had to be careful, make sure that wasn't just a 1, because that would have been an integration where you get a natural log of an absolute value. All that stuff will continue to be in play. All right. So let's move on. Same topic, but moving on a little bit. What do you mean a little bit? Every single one we've done so far, all 5 of these, have been definite integrals. I'm sorry, indefinite integrals. We're about to get to definite. So far, these have all been indefinite integrals, which means you need a C in the answer unless they give you an initial condition to match. Then you can actually algebraically find the C. We've done that. But for definite integrals, when we're doing the substitution technique, not only do we have to make sure that all of the x's turn into u's somehow, that we don't have any x's available, you will have endpoints. The original endpoints are in terms of x. You should, because it's the best process. Now, notice I'm saying should. There is a way to do this without what I'm about to say, but I'm going to emphasize doing it this way. Because if you don't do it this way, it plays a little differently. So you should convert the endpoints to values of u, i.e., plug in the upper and lower bounds, the let statement to get the equivalent u value. So when I tell you to integrate from 0 to 5, those are in dollars. When you say let u equals blah, 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 you're going to yen. $0 and $5 are not the same thing in yen. It's roughly like what, every penny is a yen? And again, roughly. So integrating from 0 to 5 in terms of x, in terms of dollars, when we switch over to u, we're probably integrating from something like 0 to 500. So the upper and the lower limits will generally change. Now, they don't have to. Notice I said, $0 is 0 yen, so that conversion would be obvious. But again, typically, the upper and the lower limits have the ability to change. Maybe both of them change, maybe only one of them changes. But you're changing what we call variable spaces. We're changing dimensions. And it's a lot fancier than how we really treat it. So this is the way you're supposed to do things. Now, notice I said supposed to, should, best, because there is a way to do this without changing. And basically what you do is you just go back to x's and then plug in the x values. But by changing to u values, we're never going to have to go back to x's. We can plug in terms of u's, which is generally a simpler looking equation or function. So let's try this out. Example 3. Evaluate definite integrals. A. We're going to do the integral from 0 to 1 of x over x squared plus 1 dx. And again, the dx go to the side or in the top with that regular x. That's x squared plus 1. All right. So this looks like a quotient. We don't know how to handle quotients, so we're going to do substitution. Let's come in and say let u equals. All right, there's a top and a bottom, so it usually is the bottom unless there's a natural log somewhere. Also, the bottom has an x squared, the top has an x, so yeah, it's probably x squared plus 1. So that would say that du dx, the derivative, would be 2x. The derivative of 1 is nothing. Multiply both sides by dx. I'm going to stop showing the basic linear algebra here. You get du equals 2x dx. Divide both sides by 2x, and you get du over 2x is equal to dx. Again, I'm going to stop showing that basic linear algebra. So the two things we're plugging in, we're going to be writing a u instead of x squared plus 1, and we're going to be writing du over 2x instead of dx. So this integral becomes the integral from, and I'm going to write a to b, because for now, I don't know what they are. We'll get to that in a second. I could go ahead and do this, but I want to go ahead and get the integral set up at least. So the x stays. That x in the top stays. I haven't said to change that. But the x squared plus 1 in the bottom becomes just a regular old u. And then the dx to the side, this dx is now du over 2x. So that's times du over 2x. And look at that, you got an x in the top and x in the bottom. They will cancel each other out. Oh, you're stuck with the 2. Oh well. So equals the integral from a to b. Now there's a 2 and a u in the bottom and a du in the top, so you can do du over 2u. My personal opinion, I like to pull constant multipliers out of the integration. So this is a half times the integral from a to b of du over u. But what is a equal to? What is b equal to? You got to plug the 0 and the 1 into the let statement to find that out. So when x equals 0, this is the bottom one. When x equals 0, you're going to plug that into the u equals x squared plus 1. We're plugging into x. So u equals 0 squared plus 1, which is 1. So when x equals 0, that's equivalent to saying that u is equal to 1. When we've changed spaces, when we've changed variables, when we've changed dimensions, when we change from dollars to yen, 0 in x is equivalent to 1 in u. Obviously, that wouldn't make sense for a currency, but again, this isn't a currency exchange. What about when the x was 1? That's the upper limit. What's the equivalent in the u space? That was weird. There we go. U is equal to 1 squared plus 1, which is 1 plus 1, and that's 2. So when x is 1, u is equal to 2. This is the a and the b, the upper and lower limits. So this is the integral. 1/2 the integral from 1 to 2 of du over u. So going from 0 to 1 in terms of x's is the same thing as going from 1 to 2 in u's. There's no x's anywhere, everything's in the same space, so we can now integrate. With a u in the bottom, that's that special case, that the exponents of 1, bring it to the top's a -1, adding 1 to that makes it a 0, can't have a denominator of 0. So this was the natural log rule. Leave the 1/2 alone. The integral of du over u is the natural log of the absolute value of u. And then we're integrating this from 1 to 2. Now we don't go back to x. That's the major difference here. Because we have the values in terms of our new currency, our new dimension, our new variable, we don't even need the x's anymore. We're just going to plug in the 2 and the 1 into this. And if you don't trust me, I'll show you that it works after the fact. So equals 1/2 times the natural log of the absolute value of 2. So that's plugging in the upper limit. Then a minus, and now we plug in the lower limit of a 1. 1/2 the natural log of the absolute value of 1. Clearly, we don't need these absolute values. So that's 1/2 natural log of 2 minus 1/2 natural log of 1. Please remember that the natural log of 1 is 0. You are supposed to have that memorized. The natural log of 1 is 0. So this is equal to 1/2 the natural log of 2 minus 1/2 times 0, which is just 1/2 natural log of 2. Please note that this is the same thing as the natural log of 2 raised to the 1/2, which is the same thing as the natural log of the square root of 2. They're all the same. But you're probably just going to stop at the 1/2 natural log of 2 in this course. Remember, coefficients can be brought up as exponents inside of a natural log, and then a fraction exponent is just a radical. All right, so in green, I'm going to show the alternative way. The way that I will never do again. So this is when I said you should convert the endpoints. You don't have to. Here is how you can do it without converting the endpoints. We had our integral from 0 to 1 of, what was this? X over x squared plus 1 dx. We still said let u equal x squared plus 1, and it ended up giving us that dx was equal to du over 2x. Those are the two things we plugged in. So now our integral is from a to b, and it's just du over u. I'm saying A and B, I'm not saying 0 and 1. If I write 0 and 1 here, it's wrong. I don't know what the A and B are, and I'm not going to find it. Do the integration. That's the absolute value of the natural, I forgot my 1/2 in the front. Sorry about that. So that's 1/2 the natural log of the absolute value of u, evaluated from A to B. Now, because I never found the u values, we go back to x. So this is 1/2 the natural log of, instead of writing u, we write x squared plus 1. So absolute value of x squared plus 1. And we're evaluating this from 0 to 1. See, I don't use 1 and 2, I use 0 and 1 because now I'm back in x's. Your numbers have to match the variable space. So this is 1/2 natural log absolute value of 1 squared plus 1 minus 1/2 natural log absolute value of 0 squared plus 1. 1 squared is 1, 1 plus 1 is 2, the absolute value of 2 is 2, so that's 1/2 natural log of 2 minus 0 squared plus 1 is 1, that's minus 1/2 natural log of 1, which we already know is 0, and you get your same 1/2 natural log of 2. Now you might say, Mr. Beckner, I think that way is easier. And if you do, then you can use it, and that's okay, but trust me, there are times when it isn't. It depends on how simple or complicated your let statement is, and how simple or ugly your endpoints are. I personally think more often than not, it's easiest and better to do the change here, because then that way you can see the numbers under the new variable. Because what a lot of students will do that try to use this method is, instead of writing A and B here, guess what they do? They write 0 and 1, then they end up plugging the 0 and the 1 into this one, and they will not get the appropriate answer. So they just go, oh, we'll go ahead and plug the 0 and 1. No, you never found out what it was equivalent in U. So you have to be very, very, very careful with that stuff. All right. I'm doing that. Give me a second. I thought I had another problem and I'm not seeing it. Actually, give me like 20 seconds. It's really weird. Now when I think I said this last time, but now when I hit mute, it gives me this scary, like, I have to confirm recording again. And now I'm terrified that I'm going to miss it because of what happened in my other class. I mean, I didn't do anything wrong in my other class. I'm just terrified of something not recording now. That was Zoom messing me up. All right, so let's try this out with a word problem. Example, I think we're up to 4. Pollution is being discharged like the rate of R of t is equal to, word rate, that probably means we're going to do a derivative, right? 400 e to the, 400t, I missed my t, 400t e to the t squared. Ooh, that looks like a familiar format. And then that's in tons. Year, t is the number of years. Let's measurement begin. Find the total amount of pollution discharged to the lake in the first 2 years. So I gave you a rate of something happening and we want the total. We have said multiple times that when you're given a rate and asked for a total, that's accumulation basically, you're integrating it. So what we have to do is the integral from 0 to 2, first 2 years, of 400 t e to the t squared dt. Well, we're going to need a substitution. We're going to say let u, and we've basically done this already, be t squared. So du dt is 2t, which means du is equal to 2t dt, which means that du over 2t is equal to dt. So that gives us the things that we need to change. So it's the integral from a to b now of 400 t e to the t squared is now u, e to the u, and then the dt becomes du over 2t. Well, the 400 divided by the 2 makes a 200, so this is the integral from a to b. 200, and the t's will cancel, so this is just e to the u du. But we got to find the a and the b. We got to find the upper and lower limits. So when t is equal to 0, that's year 0, plugging that into the let statement, u would be 0 squared, which is also 0. So that's the a. When t is equal to 2, your u is 2 squared, which is 4, so that's the b. So this is the integral from 0 to 4 now, not 0 to 2, of 200 e to the u du. If you like pulling out the 200, be my guest. I really only mainly focus on doing it when it's a fraction part, but it's still cool to do it this way. 0 to 4, e to the u du. The integral of e to the u is e to the u. We don't need a plus c because it's a definite integral. So 200 e to the u evaluated between 0 and 4. So this is 200 times e to the 4th power minus 200 times e to the 0th power. And remember, anything to the 0 is 1. So this is just 200 times e to the 4th minus 200 times 1. Just 200 e to the 4th minus 200. Now there's your analytic answer. But of course, this is an application, so we probably want to approximate this by jamming it into a calculator. So we get our calculator. This was some stuff from my last class. 200 e with an exponent to the 4th power, close the parentheses, minus 200. Make sure you know how to type all this stuff in your calculator. And you get 10,719.63. And we're going to round this to the nearest whole. So this will be 10,720. So that would be in tons of pollutant. Sounds terrible. So calculator, let's graph the original function to show you what we're representing. We had 400, I got to use x instead of t, and then times e to the x squared. Oops, e to the x squared. Close it, close it. Let's start out with a standard zoom and see what we get. Well, we don't even really see anything. The reason being, there's a 400 up there, so we probably need to make this window. In terms of the y values, we only need to go 0 to 2. So y minimum, 0, y maximum, 2. I'm sorry, those are the x's, not the y's. Bah. 0 to 2 for the x's. The y's, we definitely don't need any negatives, so 0, maximum. Well, that's probably going to be some big number. Let's try 10,000. Well, the total of it was 10,700, 200, so let's try 20,000 to start off. Let's see what we get. And you can see that this thing even still grows way beyond what I've got. If I hit trace and type in 2, we get 43,678. So let's go to 45,000. The program runs a lot slower than I can do this by hand. And you can see your exponential curve, the explosion taking off, because this pollutant just keeps dumping in at an accelerated rate. Hopefully somebody stops it at some point. So this was the growth rate. So at any point along this curve, that's how quickly the pollutant is going in at a changing speed. So integrating this, getting the area under the curve would give you the total pollutant over that amount of time. So if we go second, calc, option 7, lower limit of 0, enter, upper limit of 2, because this is not in U's, this is in X's. So big numbers, it's going to take a minute to calculate. Yeah, 10,719.63. Same answer. So that's the total pollutant. Again, when you're given a rate and asked for a total, you are integrating. When you are giving a rate, and it might not even say the word rate, you might just need to use clues like the word per is in there. That's a rate. Or a number of years since. That's another thing that might denote a rate. Doesn't always, that last bit, but it can. All right. So that will close out .5, integration by substitution. And I believe the last section we're going to cover from chapter 4 is 4.6. I'm confirming that real quick. Yeah, 4.7 is on numerical integration. That's more of that stuff like from 4.2 where we had the rectangle rule, and I said there's also a few others like a trapezoid rule. There's also something known as Simpson's rule, which we're not going to get into that, but there are many different ways besides just rectangles for doing numerical integration, for approximating the area under a curve. And again, in this course, we want to focus on the analytic methods because we're not really teaching you how to do a bunch of computer programming and spreadsheets and stuff like that in here. All right, so save. Please don't crash. Please don't crash. All right, new. So last section of chapter 4, not necessarily the last section of the next test though. Again, we'll talk about that more next class. 4.6, integration by parts. Let me tell you, this is not the easiest method. Sorry, where'd my page go? Here we are. Integration by parts. So this is another scenario for integrations that feel like products, quotients, chain rules. However, sometimes it's needed really simple looking integrals that don't follow previous rules. Lots of space. Oh yeah, Word's about to crash. I love technology. There's not even a title up here. I can't change the maximizing. I wish it would just go ahead and crash. Let me copy paste this. Maybe I can force it to crash. That's me clicking heavily. I really don't have time to waste. Thank you, technology. Are we having fun? All right. Okay. Let's try this again. Oh, that's not good. Sorry, I want to make sure that I don't file saved. All right, it did. What did I just do? Darn it. I didn't mean to close the whole thing. And what? No, it's not there. Oh my Lord. Oh my Lord. All right. 4.6. Sorry, I'm frustrated. Integration by parts. This technique is another. This is going to be paraphrased because I didn't have this written down. I always just fly from the hip. Is another technique used when it looks like a product, quotient, or chain rule. Sometimes it's used for simple looking integrations that don't follow previous formulas. What we're going to do is we're going to do the proof of this. This is one that I feel like is necessary to do, and it's not the prettiest thing in the world, but we're going to do it. So let's borrow product rule derivatives in the following form, ultimately solve it for, there's two things you can solve for, but one of the, hold on, I'm trying to say too many things at once. Let's borrow the product rule for derivatives in the following form and integrate it. Then solve for one of the resulting integrals. So the product rule states for derivatives that if you have something written as a product, and I'm going to use the letters U and V because that's what the letters are going to be seen in this. It's because it kind of feels like a substitution, but it's kind of not. So the derivative, this is me saying the derivative of a product. So that's the derivative symbol of a product. It's, and we've been saying it's the derivative of the first times the second plus the first times the derivative of the second. And we've said there's like 16 different ways to write that. That's the one I'm going with. Let's integrate both sides. Integrate this. Over dx, which was the original variable. I'm not going to be able to fit that in. Whenever you have a derivative of something, a derivative of something equal to something else, if you integrate it, you get the regular function. So what we're doing, we're taking that black handwritten stuff, and we're just going to integrate both sides. Now, when you integrate, you have to throw in that dx, whatever variable you're integrating over, because we're not going to see u's and v's in the problem, we're going to see x's. So the left side is the integral of u v prime times dx. The right side is the integral of u prime v plus u v prime all over dx. Again, all I did was I took this right here and I integrated both sides. Whatever you do to one side, you do to the other. That's a rule of algebra, right? You can take a derivative of both sides, you can integrate both sides, and we've done this before. Now, please note that when I write u prime, that is really du over dx in differential format. And when we write v prime, that's really dv over dx. Because we're going to need this notation to kind of clean this up. So all the primes, I'm going to do a replacement. So this becomes the right-hand side. Hold on, I don't want to write just the right-hand side. I want to write the left side. The integral, and it's no longer an integral, blah. Because we're integrating a derivative, the integration of a derivative is itself. There's no product rule needed because this was the derivative of a product. So the integral of a derivative is itself. The left side is just u times v. Since I've changed something, I'll switch colors. We integrated the left side to get that. Equals. Now on the right side, where I see u prime, I'm going to write du over dx. When I see v prime, I'm going to write dv over dx. So integral, parentheses, u prime, blue for changing. So that's du over dx times v. And then plus u times v prime, that's really dv dx. And then there's our parentheses closing and the dx. Let's let's make this two separate integrals. Let's separate the right-hand side. Separate, abbreviated, the right-hand side. So what we'll get is, now I'm not changing the left, so I'm going back to red. uv equals integral of, I don't need the parentheses anymore, I'm just distributing the dx. I'm just giving the dx to both of these bits. That's all we're really doing, and we're going to make it two integrals. So this is now the integral of du over dx times v times dx. Again, this dx has been given to the first term. Now, since I've got my dx, I close the integral. So we go plus integral u times dv over dx dx. Again, the main thing that's really happened here was I distributed the dx, and now that I have it distributed, I make it two separate integrals. Well, look at this. You got a dx in the top and bottom. You got a dx in the top and bottom. You can cancel the dx's. So now what we get is uv equals again, I'm canceling the dx's. Those are gone, and those are gone. So the integral of duv, which is a weird format, du times v specifically, plus the integral of udv. I'm just going to swap the order in the first. So what we get is uv equals the integral of v du plus the integral of u dv. Now what we do is we're going to subtract one of these two things. It technically doesn't matter. We're going to subtract the integral of v du, though. This is just how most mathematicians do it. We're going to subtract the first one. So we're going to subtract minus integral of v du minus integral v du. What this gives us is uv minus the integral of v du is equal to the integral of u dv. All I'm going to do is swap the order of the left and the right side. So what we get is the right side, integral of u dv is equal to uv minus the integral of v du. This is a formula for integration by parts. This involves two substitutions and some extra stuff. Some extra stuff. Oh no, when I made a new page, I didn't hit enter 10 million times. Ay, 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 ay. Fudge. Okay, for some reason hit enter didn't but push everything down. I really have a hard time predicting how Word is going to work sometimes. Because sometimes when I hit enter, it makes all that stuff go down. It's weird, it's wacky, it's wonderful. All right, so this is going to involve two substitutions. We'll have a let u equals blah, 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 blah. And we will have a let dv equals blah, 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 blah. You will need to take the derivative of u and solve it for du. Then you'll integrate dv to get v. This problem is all over the place. That's why I'm just going ahead and flat out putting the techniques up front before we start doing anything. And I think we'll get to one of these today. So what in the world is this formula, the integral of udv? But Mr. Beckner, you said these variables had to match. That's kind of the point. Now, your original problem is all going to be an x, but you're going to do two different substitutions. One of them is going to be a u, and one of them is going to be a dv, not a v, a dv. And then for the u, you're going to take its derivative, and instead of solving it for dx, you'll solve it for du, because the du is part of the formula. It's not a dx, it's going to clean up things. And in this formula, you also need v, and the way we get v is by taking the dv part and integrating it. What this formula, again, enables us to do is integrate products, quotients, chain rules that don't work under a normal substitution, but might work with this advanced technique that involves a derivative and an integral and then another integral. The reason it's called integration by parts is this first term, this first part, is already integrated for you. There's nothing else you'll have to do. You just plug in whatever u is and whatever v is. In the u, you will make the statement, let u be this. The v you'll find after you make your let dv statement and integrate it. But this last part is not automatic. You'll have to plug in the v and the du and then integrate that. So again, part of this initial process will involve a derivative and an integral. You plug things in here, and then you will actually end up integrating part of it. Again, this first part does not have an integral. The second part does. This, again, is typically used when substitution fails. This is generally used when a basic substitution technique fails. So if you were approaching a problem and you said, I don't know what to do, what should I do? And you've got a list of options, I would try a regular substitution first, and then I would try integration by parts. What integration by parts is good for is when what you have, you don't know how to integrate, a substitution doesn't help it. But maybe if you do this weird thing, maybe this new integral will actually be significantly easier. That's what we're hoping. We're hoping that we'll turn an integral that we have no idea how to handle into part of something that's already been handled for us, and then another part that'll be much simpler. So let's do one example. Let's try this out. Make sure I got lots of enters here for later. Example 1, integrate. I'm just gonna, how do I wanna have this set up? I'm going to copy this, just put it here, and then remind us what the formula is. That the integral of udv is equal to uv minus the integral of v du. It's kind of got this bounciness to it. udv, the other integral is v du. It swaps them. This right here is just the product of the u and the v. You have to memorize this. That is supposed to be memorized. So for example 1, A. We have the integral of x times e to the x dx. Mr. Beckner, we did that with substitution last time. No, we didn't. That was e to the x squared. The irony is, the simpler exponent makes this problem much worse. If you try a normal substitution, you'd let u be the x. Taking the derivative would be a 1, and there'd be nothing to cancel this x down here. So that says, nope, we need to go to this other technique. So here's one of my flares, as I like to say, my warning signals that substitution is going to fail. This and this are not off by a power of 1. That's usually what happens in a product. Now, if it was a quotient, that's not necessarily the case, and we have seen an example that way. But that's what says the normal substitution technique is probably going to fail. And let me be honest, for like a third of the problems that end up needing to be done by parts, I would try substitution first, I would hit a dead end, and then I'd go back to integration by parts, or go forward to integration by parts. So these are the two lets we make. We say let u equal, and I'm going to make a statement about what should be what ultimately. This one is set up in a more proper format. The u needs to be the x. And then we're going to say let the dv be everything else. So I'm going to write this part down after trying an example. So let dv be everything else, the e to the x dx. The dv has to have the dx. That is 100% of the time, because when you go to integrate it, you need both of those differentials there. So for the u, we said we take a derivative. You will need to take the derivative of u. What in the world? Select. You will need to take the derivative of u and solve it for du. Then you'll need to integrate dv and solve for v. So let me just make sure I copy paste that there too. So take the derivative of the red part. So du dx equals, well, the derivative of x is 1. Solve this for du, so multiply both sides by dx. You'll get du is equal to 1 times dx, which is solved for du. Du equals dx. This means they're changing at the same rate. It's an interesting scenario. This is what we're going to need along with this. Now for the dv equals e to the x dx, you integrate both sides. Integrate dv, integrate e to the x dx. Integrating a differential just gives you that variable, so the integral of dv is v equals, and the integral of e to the x is e to the x. Skip the plus c part for this. Right here, we're just going to put the plus c at the very end of the problem. So in this part, what we need is the dv is equal to blah, 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 and what the v is equal to blah, blah, blah. Those are the 4 bits we need to plug into this formula. Now we're not plugging anything into the left side. The left side, the x was the u, the e to the x dx was the dv. So this is the integral of x e to the x dx. That should now be equal to formula. U times v. Here's your u, here's your v. Multiply them. But don't write u and v, write the things in terms of x's. So x times e to the x. Again, this right here is the uv from the formula. The u, we made the statement about, but the v, we had to integrate the second statement to get it. Then there's a minus, then there's an integral symbol, and this goes v times du. So V times du. What's interesting is you don't plug in the dv into the right side of the formula. It's just necessary for the left side. So you don't even end up using this part for the plugging in. It was just critical at the beginning. I don't even necessarily need that circle because of that. So minus the integral of v du. The v was here, so that's e to the x. And then the du, that was this, which is just dx. u v minus integral v du. And the good thing is the integral that we're left with is simple and we know how to handle it. That's the point of integration by parts. We didn't know how to handle x e to the x, but we do know how to handle e to the x. So this becomes x times e to the x minus. Integrating e to the x is literally e to the x. Now we did the integration in the problem, so we put our plus c, and guess what? That's all you can do with it. That's the answer. So again, how did we use this? We say let u be the spoilers. It's generally simpler looking part. So when I say simpler, what looks simpler, x or e to the x? X looks simpler. After that, we say let dv be the rest of the problem. After that, we integrate dv to get v. After that, we take the derivative of u, solve for du. Again, there's one major difference between substitution and integration by parts. Substitution, you're solving for dx. Parts, you're solving for du. Just do this. I want this all together, so let's remove the space. Perfect. Special note though. If the natural log of x is involved, u is generally the natural log of the x. Typically. Kind of like with the substitution technique, when the natural log was involved, we usually let the u be that. It's the same thing here. So if you have a problem that you think you need to do with integration by parts or substitution, and it's got a natural log somewhere, the u probably needs to be the natural log of x. Again, I said typically, there's exceptions to every rule, but this is what you would expect in homework tests. All right, so I do need to start getting ready. I'm sorry, for something else. Blah. Just on my schedule that has nothing to do with tomorrow. So I do need to call it a day there. We will practice this plenty more next week on Tuesday live. But for now, I'm going to go ahead and upload this. So it should be up in 30 minutes. Not that you can, this conversation is really necessary. Since when you see it, it'll be up. But we did finish the 4.5. So remember that that homework is due a week from tomorrow's class, which is the 23rd. So remember that 4.5 is due on the 23rd, and I think a couple other homeworks were due tomorrow, but that file closed out. Come on, let me see my desktop. Let me see my desktop. And it did, wow, just wow that it didn't save. All right, either way, all the stuff up here was accurate. Ignore the 154, that's my other class. Yes, 4.3 and 4.4 due on the 16th. I'd originally had 4.3 set as another date, but I fixed it. And then 4.5 due 7/23. There we go. So that's the 7/16. Boom. So on that note, have a good one. We'll pick up where we left off next time, and we'll do a full class next time as well. No more issues, I hope. So take it easy. Have a good weekend. Email me with any questions. I think I said I might not be able to get back to you until maybe late Sunday or early Monday due to going out of town and not having internet. But I will get back to you when I can. Take it easy.